Hi, good morning. Yes, last year I gave a presentation about digital audio workstation architecture, just a good primer, and I'm carrying on since I got quite good feedback on that one and going deep on evaluation and evolution of architecture. So, who am I? I'm Ilias Bergström. I'm a computer scientist in training, always focusing on audio and graphics technology. I've always worked in this field as well. For the last 5 years, I worked at Elk Audio. You might have seen me at the last 5 ADCs. I started off as senior and later went on to working as a lead dev there. Before Elk, I worked with Planetarium Software for 2 years, doing work across the code base, also very much modernizing their audio engine. And I have a background doing research for about a decade, a PhD, 3 postdocs, where I combined engineering, interaction design, and also, I would say, some art practice applied to media technology and virtual reality. Since very recently, I no longer work at Elk Audio, but I will be mentioning the work that I did there at this talk. So, yeah. Last year, I gave a talk about the architecture of digital audio workstations, which was a broad introduction and an overview of the architecture of 2 DAW applications. It covered a great deal of ground, considering it was a single conference talk, but I left a lot of important topics out. So this talk, I address that, and I cover the next most important subjects in relation to software architecture, which is evaluating architectural decisions before actually an implementation is made, and also evolving architecture, which is just another way of saying that it's evaluated continuously as requirements change and software evolves. So, why bother? Hopefully nobody would object, but I've seen many comments and had several conversations along the lines of, why make things harder than they need to be? Just bloody write the code already. And I'd say it's all about just enough architecture and design. It's, as you know, I would say a good way of summarizing what we do as developers is much of our work is managing complexity. I've worked on code bases spanning more than 1 million lines of code, which just emerged and evolved from successful small projects, and which eventually became very, very hard to understand over the years because there wasn't really any conscious thought on the architecture and design of the software. And I've also created several large applications from scratch, and I've learned from many mistakes along the way. And simply put, I think that even the smartest person among us has limited capacity. Our brains aren't infinite. We just can't cope with any amount of complexity. And to deal with complexity, we need to divide and conquer and use repeated patterns and recurring ideas in the overall architecture and design. These need to be carefully selected, documented with just enough detail so we can understand our code and explain it to others. And it's a bit of a cliche that bears repeating, I would say, that code should be written mainly to be read. Of course, it needs to run a computer, but it'll be read many, many more times than it's written or modified. So there's an important definition that I didn't spend time on last year, and now I want to give some more time to explain. There is a distinction between architecture and design. I'll start first by defining what architecture is, and we'll get on to that. At last year's talk, I used the definition that software architecture is the set of structures needed to reason about the system, which comprise software elements, relations among them, and properties of both. This is from a textbook, Bas, Clemens, and Kazman. And since then, I've done further reading, including the Fundamentals of Software Architecture book and its follow-up, Software Architecture, The Hard Part by Richardson Ford and a few others. And in those, the authors also very helpfully give the first law of software architecture, which is that everything in architecture is a trade-off. And the second law, why in architecture is more important than how, though you have to get to how eventually. And they also state, in other words, architecture is about the stuff that's hard to change later. And I wish I could summarize the books, but no, there's just too much in them. I definitely recommend reading them, or at least looking up a couple of the conference presentations of the authors. There's a lot of really good stuff in there. And getting to the point that I wanted to stress a bit more this time about architecture versus design. What do these two words mean in our context of software engineering? Richards and Ford say that it's a constant struggle for architects to keep architecture and design as separate but related activities. And very unhelpfully, they don't give precise definitions. They just don't want to wade into the never-ending argument, their quote. And they add that architects must understand design to implement the solutions that they need. But first, they need to understand why one choice has better trade-offs than another. I was also very interested in learning a bit more about software architecture and software similar to DAWs, but a bit further from our industry. So I went on and researched what books there are on the topic. I found that this one is probably the most popular and well established in its field. It's 1,240 pages, but I would say the author really only mentions one software architecture pattern in the whole book, layered architecture. Then he briefly touches on design patterns, but only really mentions iterator and singleton. And actually, to my personal disappointment, the only example uses of singleton are actually widely considered anti-patterns. It's like, just don't use singleton for those things. Please don't. There's a million other good things that you can do instead. But no, he just says, yeah, use singleton for that. Great. Anyway, but besides that, the rest of the book is really, really important, useful information about low-level optimization, memory management, lock-free programming, all the really nitty-gritty of how you make a game engine that works and performs efficiently. And don't get me wrong, these are really important topics, and it is a very good book. I very much recommend it. But I would say its use of the word architecture really doesn't follow the definition. I would probably maybe change the title, but the content is fantastic. Or rather, maybe it doesn't conform to the definition of Richards and Ford and the use of the architecture definition in the broader industry of software engineering. So maybe my talk title should say architecture and design, because I will be talking also about design a lot today, just as I did in the previous talk. Anyway, so definitions apart, what does it mean to evaluate architecture? So to evaluate something, you need criteria. What informs the architecture? You have functional requirements, what the software needs to do, and you have design constraints with 0 degrees of freedom. It's like, you need to run on this embedded platform. That's your constraints. Things like that. These are used to formulate what's called quality attributes. What is a quality attribute? It's a measurable or testable property of a system that's used to indicate how well that system satisfies the needs of its stakeholders. Richards and Ford call these architecture characteristics. I managed to say that. I will stick with quality attributes because I'm not sure I'll be able to repeat that phrase correctly. And I also use it in the last talk. It's a bit of a tongue twister. Anyway, the most commonly used QAs are availability, interoperability, modifiability, performance, security, testability, usability. You use the ones that best apply to your system at hand, but these are the most common ones. And then the main take-home from Ford Richards' books is that architectural decisions are always about balancing between different sets of trade-offs. There's no silver bullets or best practices. It always begins by qualitatively analyzing the specific problem that you have at hand, which only you really need to solve, and there's not really a long history of people solving that exact same problem. Your problem is unique, and you need to think about it uniquely every time, which is why architecture is hard often. And the architecture decision space is influenced by three interlocking forces. You have communication that can be ranging from synchronous to asynchronous. You have consistency of the model or the data, which is atomic or eventual. And you have coordination, which can be choreographed and orchestrated. And choices on one of these dimensions affects the other two. So it's always about trade-offs across several dimensions when you start thinking about your architectural choices. And while these books only ever really discuss these trade-offs in relation to distributed software, huge microservice architectures running on several computers across the globe, and it's back-end code and front-end code and, the kind of stuff that we don't do. I would say that a lot of what they cover applies equally well to desktop software or embedded software, like, for example, DAWs. I think the information in those two books translates very, very well. So what about evolution then? Evaluation is needed throughout the lifetime of any software application. Software is, of course, initially designed. Sure, you might start writing code early, but some design upfront is necessary, especially if it's going to be a big project. And of course, while maintaining the software as requirements change, and they invariably will. Another overused quote that I still love repeating: software is finished when no one uses it. Kind of makes sense, doesn't it? So, to keep up with the theme from last year's talk, I want to show you my absolute favorite Japanese toy robot. You might see the relevance to the talk, you might not. Look at it, it's awesome. It's the Valkyrie from the 1980s Macross TV series. And you know something is completely made up when the design successfully implements all features without any trade-offs. It's a robot, it's a Gerwalk, they call it. It can fly in all of these modes, it just does everything. I'm sure the engineering team is very, very good who made this. Or maybe they never asked anyone. Anyway, so a brief recap: the two applications that I talked about last year and that the examples will be covering. First, there's Sushi, which is Elk's headless DAW, and it's central in the audio operating system of Elk. It's appeared at ADC already 4 times, from 2019 until just now, and earlier at the conference, of course. It's a live DAW, so it's more like main stage than Apple's Logic. And that mainly means that it lacks any timeline implementation, and it doesn't have a graphical user interface. It's a headless DAW. Its main purpose is for embedded use in standalone embedded hardware and embedded as an audio engine in desktop applications and DAW plugins. And yeah, by headless, it doesn't have a GUI, but it's controlled over RPC calls. We had a talk about that a couple of years ago. I think, 2022 with my colleague Gustav Andersen. So the other application I call 2. It's what I call a media control workstation. It's a passion project of mine. I've made it all myself and simply love it too much not to keep working on it. It's like a DAW for all time-based media. It's mainly for all types of control signals like OSC, MIDI, SACN, etc. So it's essentially everything that a DAW is, except it lacks any audio engine. Everything else. And also it implements many use and engine patterns that you see also in other time-based media applications. So 3D animation package will have many of the same features. Or, for example, a lighting show control application much of the features that you see on screen on a DAW actually are very much prominent also in these other apps. And this kind of is do-it-all bridge between media, I was thinking. Anyway, enough about that. What's interesting to start thinking about now is what were the requirements going into them? Why two different DAWs to begin with, or applications? After my last talk, I still got the question, why two different DAWs? Sushi and 2 are very different. Both are sort of DAWs. Where they differ wildly, and you'll see why, is in requirements and the resulting trade-offs. And I would say also there's very little overlap between the target users. If anything, I'd say I could integrate 2 to control Sushi. Maybe one day Sushi can be the audio engine that 2 lacks, and 2 can be the GUI that Sushi lacks, and the timelines and whatnot. So I could add, of course, this is a conference talk. The quality attributes that I will be discussing are cursory. It's all that I have time for, but they do fine as examples. I'll start with the ones for Sushi. Sushi is highly optimized for embedded hardware platforms. It has limited resources available compared to a desktop computer. Latency and CPU efficiency are the top priorities. And it's for standalone instruments, effect pedals, PA speaker arrays, or even wearable devices like headphones. So, the interoperability QA, it should directly interface with ultra-low latency audio frontends and also support standard audio frontends across desktop platforms, also MIDI on embedded and desktop, and it should be able to host plugins in a number of formats. In terms of modifiability, it needs to be very easily portable to new platforms, which may or may not have their own audio and MIDI front-end requirements, and it needs to scale for their resources and needs, and support plugin formats when the need arises. So you should be able to easily add new formats, is what this means. In terms of testability, we had at ELK a requirement for very high unit test coverage, real-time and non-real-time integration tests, full system tests. So that influenced quite a lot how it's designed. And usability, this is an important point. It's not an end-user application. So the usability requirements are with developers in mind. The product is for third-party developers to use Sushi and embed it in their products. So it needs a very clear API. It needs to be easy to build, update, and maintain. And it needs to be predictable through changes. All of this is still usability, but the target audience is developers. So these are the usability concerns of developers. Now going on to 2. Sure, it is a real-time high-performance application. It needs to receive, generate, modify, forward, record, play large amounts of control signals at interactive control rates. It doesn't deal with audio rate data. The UI should feel real-time. It's meant to be usable as a live performance instrument, a bit like, Ableton Live is used on stage. And yeah, that's it in terms of performance. In terms of interoperability, again, it needs to support the most widely used control data protocols. Even if some are initially supported, the architecture needs to support adding more. Modifiability, it needs to allow for adding modules that support new control data protocols via plugins and expose core functionality for end-user innovation, end-user programming. And now, the point of usability. This is not meant for developers, it's meant for end users. And it's a particular kind of end users. It's more of an end-user innovation application. If all you need is a traditional DAW, that's what you're going to use. But if you need to do something that you can't do with a traditional DAW, like, control projections and music and the lights from the same application, then you will use this. So as an end-user innovation tool, usability is different from, say, Spotify on your phone. The literature from the new interfaces for musical expression community, I'd say, is the most applicable source of knowledge for this context. Again, too vast a topic to even begin summarizing, but I recommend one of my favorite research papers on from this community. Usability, well, from the Kai community, usability evaluation is considered harmful some of the time by Greenberg and Buxton. It's a very good paper that introduces the trade-offs that go into this kind of user experience design. And I also recommend the Sketching User Experiences book by Bill Buxton. If you don't know him, he was head of the team that implemented Maya 15, 20 years ago, the 3D animation package, back when it was owned by Microsoft. And they did a lot of really interesting, groundbreaking work. So before going into the examples, I want to introduce the concept of architectural decision records. It's a great idea to keep these. Sure, we're always sort of documentation averse, but I'm not so much documentation averse as really mindful of writing exactly the right kind and amount of documentation, and this is something that I think is a very good idea to do. They're about writing the outcome and process leading to architectural design choices throughout software's lifetime. Otherwise, the outcome of the process of thought that went into a decision will be the thought process will be lost, knowledge will be lost, and the reasoning will become legacy and eventually debt. There will be decisions in the code that you can't really reason around why they were made to begin with. So here's a very simple example of what an ADR can be like. You have a title, status, the context, what forces the making of the decision, what was the decision and the justification for it, what is the impact of the decision. You can add a few extra sections, compliance notes, and each ADR can be a page or less. It's not about writing long essays that nobody reads, it's about keeping track of very important decisions. And now, about time, I'll connect practice to theory through a number of examples, starting with how changing requirements result in architecture and design changes. So, as I mentioned, Sushi was originally designed to run as a standalone application. However, years later, for internal and client projects, it had to be refactored to be used as a library and run inside a DAW plugin. And the need arose for what we called reactive frontends for audio and MIDI. What reactive means is it does not directly interface with audio hardware through an API. Rather, it is invoked through a host audio callback. So it doesn't own a clock, so to speak. It doesn't know exactly when each invocation will come. Rather, it expects one from outside, which may or may not come depending on, for example, if the plugin is paused in the DAW. All of these considerations come into account. So for long, Sushi had a main function, which was responsible for reading and parsing the configuration, instantiating the various frontends for audio, MIDI, and control, running the main loop, deallocating and shutting down, which is quite a lot, but originally it was small, so it was fine, you know, a couple of hundred lines of code, until a few years later, it was not. So it grew and grew and became what I would say a great application for the techniques in the book Working Effectively with Legacy Code. And it had to be split up. So the decision was made that the main method's ownership of the main loop and of the various subsystems moved into a class named Sushi, which contains and owns all of these instances. And in turn, this Sushi class is not instantiated directly. You don't just write, you know, make unique Sushi, but you have a configuration that you might read from a file, you might receive it over gRPC, you populate a struct, you pass that to a factory base class interface, and that factory assembles Sushi and gives it to you. Here, we have the well-known Gang of Four design pattern factory here. Well, this is not exactly the pattern itself, but our use of it. You have the factory interface, and then we had three different factories. One was for the original standalone use, where Sushi was, the standalone application. Reactive is the factory you want to use when you are embedding Sushi into a plugin or another application. And offline is for when Sushi is running in a test harness and is receiving audio from a file and writing to a file in integration testing, for example. And the configuration file, you can pass it from JSON or you can get it from somewhere else and use an explicit configurator to actually configure the instance. So, not much more to say about that other than it's worth pointing at what an ADR for this would look like. The context is the main method we've realized now has grown into having too many responsibilities, and Sushi needs to be embeddable as a library. And instantiation and configuration has over time grown into being complicated and error-prone. It wasn't in the beginning, but it became over time. And now we were at the point where we needed to make a big change, and we didn't just want to keep this old main method. So the decision was made to break it up, as we see in the record, and I've documented what was done. And the consequences are worth covering. Unit test coverage improved a lot because that main method was sort of by definition not unit testable. So now we could cover the brittle instantiation and configuration parts as well. Those weren't necessarily sources of many bugs over the time, because the bugs that I actually found doing this work were sort of off of the golden path and very weird edge cases. But still, actually doing this refactoring, I did find some bugs. And with unit tests, these bugs are not likely to reappear. And of course, also the code is much easier to read with improved separation of concerns. And it became easy to achieve the goal that triggered this process of adding complex new front ends and controllers for reactive use, which were lacking. So let's look at adding a new feature that requires designing around the existing architecture and finding a good compromise between refactoring and new requirements. Originally, Sushi was designed without any send-return functionality in its audio graph. It wasn't needed for the use cases that it was originally made for. But then eventually it was requested and needed. And considering that the audio graph had initially been implemented purely with the absolute lowest latency possible, and that was the main concern, there was again need for some compromise. We didn't want to replace the existing design. We already had clients that were using it, and they didn't need send return to begin with. They just preferred the simplicity of the existing implementation. And so the decision was made to instead create internal send return plugins rather than actually have the functionality built into the audio graph. There was a latency penalty of a single buffer following from this implementation, but the upside is it's only used if it's needed, existing code is unchanged, and the effort is quite small to make this because it's not a big refactor of the audio graph. Dave Rowland's audio graph talk from a couple of years ago is wonderful. I recommend it. I will not go into the details of the requirements of an audio graph. Just please refer to this one, 2020. And I could also say this particular work was done by my colleague Gustav Andersen at ELK. So unlike the rest of the work that I'm discussing in this presentation, I didn't do this myself. So the ADR on this, I already covered the points, so I'll skip reading them out loud, but good to have one for each point in this presentation. So let's look at how an existing architecture supporting adding a complex unpredicted feature for a lot of the work needed up to a point, and what happens then. So in 2, initially I just made 2 as a live sort of application, and then I figured timelines would be a very good idea to allow recording, playback, editing of control data, ask, DMX, you know, the stuff it supports. And the original architecture was permissive enough to allow making this change without significant alterations. Let's get back to one of the fundamental design patterns that I also covered at the last presentation, but since it's so important for this point, I want to recap it. The composite pattern, it's from the Gang of Four book, 90s book, much of the knowledge still relevant. What is the composite pattern? It composes objects into tree structures representing part-whole hierarchies. And it lets clients treat individual objects and compositions of objects uniformly. So it's very good for building a tree structure of your model, for example. And it's ubiquitous in most GUI frameworks, maybe all of them. No, there's some exceptions, but yeah. You will have come across the composite pattern if you use, for example, Juice or Qt. Besides composite, I added to my tree structure model a string ID for each node, which makes it easy to address each component over ask, so you can also remote control parts of two, and a listener list for change subscription on the nodes, so that, you know, when a node changes, you can reflect that change, for example, in the user interface. This is convenient and efficient enough for a few hundreds of components or nodes, and it's very simple and reusable and recognizable across code. But specifically for keyframes, I decided to break with that model because there was a snag. So using this composite pattern, although I hadn't really thought of adding timelines when I made the decision to use it, because I had used it, actually adding the timelines themselves and everything in the GUI, etc., was very straightforward, and reusing a lot of the code I had for serialization, for interfacing with the Juice GUI, all that. The only problem was for recorded keyframes, this model was too slow and memory intensive because a recording can potentially contain millions of messages. If you want to record ask messages over an hour from a source that generates many, you're in for receiving a lot of data. And ask isn't really so memory optimized in terms of actually storing it. It's more meant for live use. So specifically for timeline keyframes, I chose to break with the composite model and just sort of duplicate the functionality, but very optimized. That's not a problem with the original design. The two can coexist. You can have the original composite for everything else in the application, and where you've identified a need for optimization, you specifically address that need in one part of the code base. So each key has to use minimal memory, no ID, no listeners, just nationally ordered by timestamp in a sorted list, meaning that it can be much more efficiently read. You can seek into it very quickly. Adding is cheap because when you're recording, you usually do it at the end. Okay, if you drag and rearrange, that's not really performance sensitive, so it doesn't matter if it needs a new sort. And it can be allocated with memory coherence in data structure through data-oriented design so that it can be efficiently traversed. I could have kept composite refactoring out ID and listeners, but this was cleaner and a change concentrated in one place, and also I get the memory cohesion quite more easily. Data-oriented design, just quickly mentioning, it's big in game engines. That's sort of where it originated, when game engines had to run on really limited console hardware. But also, for example, Arthur discussed this on Monday in his ADC talk. Look into data-oriented design if you are not familiar with it. And what I now have is really good satisfactory performance, so I stopped here. I write 2 in my spare time. I don't need to optimize it fully. If this was my day job, I would have gone the extra mile of using custom allocators and tweak the element size of each key down to the absolute minimum. But this is good enough. Now you can record 1 million keyframes in 2, and you get manageable RAM usage. So I'm happy. The ADR, I'll skip over. Repeats what I've already said in the slides. So let's look at how to address designs that are not optimal. What do you do when you find a design that was, when it was taken, maybe good, but when the decision was taken, it was good, but now it's actually, over time, become debt in the code base. It bloats the code and results in needing to eventually perhaps change and refactor. So yeah, mistaken designs create I just said that. So in the first example, I'll just say that in the end, the change wasn't necessary and I chose to live with it. It just wasn't worth the effort yet. In 2, the visitor pattern is used to iterate over the composite structure of the model. The visitor pattern, again, a gang of 4. If you have a composite structure or any other data structure, but it's very often used with composite, you can use a visitor to traverse it. It represents an operation to be performed on the elements of, for example, a composite structure. But you can then separate the operation from the model itself. It's originally a gang of 4 pattern. It's very verbose and coupled. This is the gang of 4 version. For example, Klaus Igelberger presents a much more modern, concise version in his talk at CPPCon 22 and his book of, I think it's 2 years ago, C++ software design. There's also the strategy pattern, which defines a family of algorithms, encapsulate each one and make them interchangeable, and it lets the algorithm vary independently from the clients that use it. So both achieve the goal of keeping the model and operations separate. And there's 2 possible dimensions of change here. We have several node types, and you have different operations on these. And both visitor and strategy achieve this goal of separating these concerns, but then each one has its own trade-off. Visitor is flexible in terms of adding new operators, but it's inflexible in terms of the addition and removal of types in the model structure. It's not impossible, but it's cumbersome. With strategy, it's the opposite. Again, you get good separation of concerns, and it's optimized for stable operations. You have a few set operations, but you can easily and with little friction add and remove types in your structure. So when the decision was made to use visitor, I was thinking that there would be many more operations and that the model would be static, relatively speaking. So I chose visitor, but that assumption proved to be wrong. The issue is, though, that strategy allows adding nodes as plugins and implementations of the operations needed in the program for these nodes also inside the plugin. So if I had used strategy, I could have easily made little plugins for 2 with new model nodes, for example, for MIDI 2.0, and the operations on these, like serialization, would also reside inside of the plugin. With visitor, that is impossible because it needs to know about the existence of all nodes. It's not, in that sense, extendable. And in this case, for now, I've chosen not to refactor 2 to use strategy yet, but I know I'll need to, so I've suspended that work. The visitor classes are getting a bit large, but the code is not so unmanageable that I urgently need a refactor. And I've postponed the refactor to the point where I actually implement this plugin API, and then I need to bite the bullet and really replace visitor with strategy because it just wasn't the right choice. Not yet, though. So it's suspended for the time being. And in the last example of the set of examples that I prepared, the redesign has been unavoidable and a valuable lesson. So I allowed a God class to gradually appear. It started innocently enough as a sort of controller class during the first implementation of 2. Probably a common mistake. You think model view controller, make a controller, and then you keep piling on responsibilities to this controller. Yes, even more. And so you can see where this is going. Each object instance in 2 had a pointer of this controller, and this controller had half a dozen or more responsibilities. I know I didn't know better 15 years ago when I did this. I know now. And it wasn't so bad in the beginning. Remember, no choice is necessarily always bad. It depends on the context. In a smaller program, a small little god may even be fine. You know, it's much better than using singletons, as they're often misused, because it allows lifetime management and it allows mocking of the subsystems that the controller exposes, even if it doesn't really allow good separation of concerns. That's the downside. But as a Trojan horse, it grew and grew and ends up having way too many responsibilities. Separation of concerns is very diffuse. And because everything essentially has a reference to everything through this, build times become unnecessarily long. And here I just had to break the controller up into separate classes with single responsibility, manageable size, and then I passed the ones only needed into the parts of the program that use them through dependency injection, which means they can be much more easily mocked in unit tests. And the code has much better separation of concerns. And the signature of the class through any class that uses other subsystems is much clearer, because you see immediately on the signature it uses these subsystems because there's accessors for setting them through the dependency injection. And build times are lower. So I just had to do that, and I did. So I'll wrap up with a bit of discussion. In a distributed web architecture and design are easily distinguished. In microservices, I've never worked with them, but from what I understand, each one is a few thousand lines of code. The API between them is clear, and crucially, it's enforced because they might even be written in different languages and running on different computers. So design, in that sense, for each of the microservices is a simpler problem, and you can easily tell them apart. But in the case of a DAW or a game engine, which is usually a single monolith of millions of lines often, the architecture is usually layered or service-based or a combination of the two. Delineation is a bit harder between architecture and design, because at what level of granularity do you draw the line? When is a decision architectural and when do you say it's a design decision? It is often quite clear, but it's not as clear as in a microservice architecture. And moreover, in this context, design can be much more involved. Actual design details, as we saw, for example, with strategy and visitor, are crucial decisions that will create debt. They do require informed trade-offs, and they are stuff that is hard to change later. So the criteria apply. I'm not saying that we should call them architecture, but I'm just saying it's a bit more diffuse in this kind of desktop or big application context. So yeah, large part of my presentation last year concerned design as well as architecture. No need to nitpick, but it's worth noting. So I'll very quickly wrap up. To connect quality attributes to decisions, in terms of the Sushi instantiation, there were quality attributes requirements for its extendability and modifiability that the refactor allowed. In terms of usability, the change with the audio graph and send return directly connects to the consistency quality attribute. And for timelines, as we saw, the existing requirement for allowing plugins is something that the strategy refactor requires. I'm skipping through these because it's kind of repeating things, and I'd rather leave time for questions. A bit more recommended reading since last time. I do recommend reading all of these books that I mentioned. And that's it for this talk. I hope you want to know more. As I mentioned, I no longer work at ELK, so if you'd like to work with me, do come to speak to me at the conference. I'm currently looking for my next job. You can go to ELK's GitHub for the sushi repository and documentation. And if you want to give to a try, it's at controlmedia.art. There's also many papers of mine that are relevant that you can look for on Google Scholar. And that leaves a bit of time for questions. Thank you.